So similarly, one can do for the energy balance and the mass balance. So what you will see for energy balance, so we can now write the energy balance in terms of the modified or new variables. So I define T star as usual as T minus Ts by T infinity minus Ts. Okay. So I define this dimensionless temperature, and I can find that the momentum balance will reduce to, the energy balance will reduce to d square T star by d eta square plus Prandtl number by 2 into F into dt star by d eta equal to 0, and T star at eta equal to 0 is 0, and T star as eta going to infinity, that's equal to 1. Okay. So that's the functional form, and once again you can find T star dt star by d eta. So if we know these two quantities, then we should be able to find the heat transport coefficient. Okay. So what is important here once again is to find the heat transport coefficient. So what was found is that dt star by d eta at eta equal to 0. So this scales as 0.332 into Prandtl number to the power of 1 by 3. Okay. So note that we never knew what this exponent n is supposed to be. So by solving the actual equations, what has been found is that the gradient at the boundary scales as Prandtl number to the power of 1 by 3. So the scaling for Reynolds number comes from eta, and the scaling for Prandtl number actually comes from the gradient. So far I asked you to assume what is the functional form, but actually the correct proof for the functional form is that the gradient scales as Prandtl number to the power of whatever exponent, and that exponent turns out to be 1 by 3, and by the way this is valid only when Prandtl number is greater than 0.6. For less than 0.6 you have a different functional difference, so this n is going to be different when Prandtl number is less than 0.6. What does it mean? And yeah, that's a property, because note that this is the solution of a nonlinear equation. So you cannot say that you will have a linear dependence on Prandtl number. So obviously it's a function. That's what I'm saying. So if it is linear dependence, then you could intuitively guess that it is going to have similar functional form with respect to Prandtl number. But then this exponent 1 by 3 has been observed only when Prandtl number is greater than 0.6, and that's not difficult to understand. What is Prandtl number? What's Prandtl number? It's Prandtl number is nu over alpha. It's actually not very difficult to understand why that's the case. Prandtl number is nu over alpha. So note that we also said that delta by delta T, which is the ratio of the boundary layer, momentum boundary layer thickness to the thermal boundary layer thickness. So that scales as Prandtl number to the power of n. So the boundary layer thickness that you are going to get, the momentum and the thermal boundary layer thickness, is now going to be dependent on the properties of the fluid. So if the properties of the fluid, is now going to it dictates the delta by delta T, right. So suppose if delta is greater than delta T, okay, suppose if delta is greater than delta T, what will be the nature of the Prandtl number? Yeah, it will be greater than 1 or less than 1. It will be greater than 1, but remember there is an exponent n, right. So if Prandtl number is greater than 1, okay, if Prandtl number is greater than 1, you will always see that delta is greater than delta C. What does it mean? So we said that the momentum diffusivity in the y direction, that is, T, that should be thermal boundary layer, okay. So the momentum transport depends upon the boundary layer thickness and the heat transport depends upon the thermal boundary layer thickness. So the length scale of diffusivity of momentum and the thermal boundary layer, thermal diffusivity, these two are going to strongly depend upon the boundary layer thickness. Now suppose if delta is less than delta T, in fact there are situations where this is the case. This is true for liquid metals. The place where it is used is the way aluminum is extracted is you have a very high temperature process where the aluminum is actually manufactured at a molten state. So you have a liquid metal which is present. So in those cases you will see that the Prandtl number is actually much smaller than 1. So there the heat transport process is completely different because the boundary layer thickness of the momentum boundary layer is going to be smaller than the thermal boundary layer. Therefore the heat transfer properties are completely different. In fact that's why the exponent is different. So this 0.6 is a special case where if you have a liquid metals where you have a very high temperature process, then the heat transport mechanism is slightly different and therefore you will see that the solution falls out to be a different exponent, and we will see that in a short while, maybe not today's lecture. I will give you what's the expression for the exponent n when Prandtl number is actually less than 0.6. Okay. So with this we can actually go and find out what is the heat transport coefficient. So the heat transport coefficient is minus k d dou t by dou y at y equal to 0 divided by Ts minus T infinity. So we introduce all the scaling and that will turn out to be Kf into square root of u infinity by mu into x into dt star by d eta at eta equal to 0, and so from here you will find that the Nusselt number is equal to 0.332 Reynolds number to the power of half into Prandtl number to the power of 1 by 3. Okay. So this half comes from the scaling that you use for eta and 1 by 3 comes from the gradient of temperature at the boundary. Okay. So the first time you are seeing a complete functional form for Nusselt number, and similarly you could find out what is the average Nusselt number. So that will once again turn out to be 0.664 into Re to the power of half. This is based on the length of the plate multiplied by Prandtl number to the power of 1 by 3. Okay. So we showed that the friction coefficient is given by 0.664 divided by the square root of Reynolds number, local Reynolds number, and we also said that the average friction coefficient is given by 1 average friction coefficient till that location, and similarly we said that the Nusselt number, the local Nusselt number is given by 0.332 Reynolds number to the power of 1 by 2 and Prandtl to the power of 1 by 3. Okay, and the power of Reynolds number comes from the scaling arguments, and the Prandtl number to the power of 1 by 3 comes from the gradient at the boundary. Okay, and so from this you can see that the average Nusselt number till any location is given by twice that of the local Nusselt number, and similarly we could write for the mass transport problem simply by using the boundary layer analogies. Okay. So we said that this is valid only when Prandtl number is greater than 0.6. So when it is less than 0.6, so what happens is that the thermal boundary layer thickness is usually larger than, for very small Prandtl numbers, the thermal boundary layer thickness is much larger than that of the momentum boundary layer thickness, which also implies that the velocity profile is insignificant. So it's almost like a flat velocity profile. So the boundary layer velocity profile is completely now not very significant, and therefore it's not going to affect the heat and mass transport process. And so the correlation corresponding to that would be, copy it, that will be 0.565 and Reynolds number to the power of 1 by 2 and Prandtl to the power of 1 by 2. So you get a different scaling for Prandtl number because the velocity is now not playing a significant role in the heat transport process. By solving the equations, you have to make an approximation. Remember, you solve the momentum equations. Now you don't have to solve the momentum equation. You assume that the velocity is constant. Right? You say it's a flat velocity profile. So now for all values of, so for any values of Prandtl number, a general correlation would be all values of Prandtl number, and that would be 0.87, 1 by 2, Prandtl to the power of 1 by 3, and 1 plus so remember that here we said that so if you want to use correlations for any range of Prandtl number, now this becomes important particularly when you have fluids which is moving, or when you have multi-phase systems where different fluids are moving, then you have a different kind of problem, and so you need to have effective Prandtl number which is based on the effective properties of these two fluids, and so in those cases you will have different ranges of Prandtl number, and so it's important to have a general correlation which works. Now this is primarily for the purposes of somebody who is working in an industry who doesn't know he cannot differentiate between Prandtl number of 0.6 less or 0.6 greater than 0.6. So it's just for a general correlation which is useful in certain calculation purposes. But for the course purposes, what is really important is these two individual correlations which is valid for different ranges of Prandtl number. Okay. Alright, so one could actually do a similar exercise for turbulent conditions. One could get similar expressions for turbulent conditions. So the friction coefficient will be 0.0592 into Reynolds number to the power of minus 1 by 5. So we assume that the Reynolds number is between 2 into 10 power 5 and the Nusselt number is given by 0.0296 into Rex 4 by 5, 1 by 3, and similarly so that's for the turbulent conditions. So note that there is no way to solve, even to get insights into the nature of the problem. For turbulent conditions, it's impossible to solve this problem even for asymptotic analytical conditions. So really it's just all of these have been obtained by solving the equations either using series solutions or numerically in order to obtain these correlations. No. Some of the approximations do change. So some of the approximations you make in laminar flow conditions would be different in turbulent flow. Suppose I have a flat plate, okay. Suppose I have a flat plate, okay, where there is a fluid which is flowing past this flat plate, and you have some region which is laminar, okay. So you have laminar conditions here, and then you of course have a transition, and then you can have a turbulent regime. So this is the critical distance at which the Reynolds number is. What's the Reynolds number? Critical Reynolds number? Yeah? 2 into 10 power 5. So that's the critical Reynolds number. So one could find, so remember that what we are interested is only the average heat transport and average mass transport coefficient. So we would really require to calculate the average heat transport coefficient for the full plate. Okay. So suppose if we assume that the transition region is very small, so remember that transition region is a flow condition which has not been characterized, and it's not been fully understood as to what is the hydrodynamic condition in the transition region. So if we assume that it's very small, then one could define average heat transport coefficient for mixed hydrodynamic condition, that is you have laminar and turbulent, simply as 0 to xc dx plus xc to L. So this is laminar heat transport coefficient and turbulent heat transport coefficient. Okay, so where the length of the plate is L, that's the length of the plate. So one could simply integrate the local heat transport coefficients in laminar condition up to the critical point and integrate the same in the turbulent conditions up to the full length of the flat plate. Okay, so that will give you what is the average heat transport coefficient when you have mixed conditions of both laminar and turbulent conditions. And one could do the same exercise for mass transport coefficient as well. So if we know Nusselt number, we should be able to calculate the heat transport coefficient under laminar conditions, similarly heat transport coefficient under turbulent conditions. So plug that in and you can integrate. So I am not going to do the integration here. It's quite easy to do this integration, it's not very hard. It takes about 5 minutes to do the integration, so you should all do this. Okay. So the average Nusselt number, which is defined as H into L by Kf, that's given by 0.664 into Reynolds number, the critical Reynolds number to the power of 1 by 2 plus 0.037 into Reynolds number to the power of 4 by 5 minus to the power of 4 by 5 multiplied by Prandtl number to the power of 1 by 3. So all I have done is I have taken the expression for Nusselt number, local Nusselt number, that is Nu laminar, that's 0.332 Rex Prandtl to the power of 1 by 3. So this is nothing but H laminar into X by Kf. So I have found out what is H laminar from this expression, and then I integrate with respect to the X coordinates up to the critical location, and then similarly I take the expression of Nusselt number for turbulent flow, that will be by Kf, and then you integrate that with respect to x coordinate going from the critical location to the length of the plate, and so clearly you can see that the second term here corresponds to the integration in the turbulent regime, and the first term corresponds to the integration in the laminar regime. You can clearly see that there is a 0.664 that comes here. That is nothing but the average Nusselt number in the laminar condition, and this is the average Nusselt number in the turbulent condition. If you assume that the properties are constant, it doesn't, but supposing if you say that the properties change with the hydrodynamic condition. No, but Prandtl number is simply defined as nu over alpha, right? So now if we said that delta by delta T is Prandtl number to the power of n, this n is different for laminar and turbulent. So that n takes care of the difference in the height. Excuse me? Yeah, that's true. So it turns out for flat plate case it's the same. So note that it's not just the hydrodynamic boundary layer which changes. This is the ratio. Be careful, it's a ratio. It's both the hydrodynamic and the thermal boundary layer actually is changing. Now when it comes to Prandtl number less than 0.6, the variations that you get in turbulent flow is very different. So you have to be careful how it is defined. This problem comes only when Prandtl number is less than 0.6.